Hello, this is Mr. Couple. This is a three-part video series showing my IBSL Year 1 students how to conduct an experiment on an ideal gas. We'll be using a PhET simulator for this, and the purpose of this experiment is to mirror historic experiments. So we want to try to get a feel for what it was like back in the 1800s when these experiments were first being done. Obviously, with modern technology and simulation magic, it's going to be a little bit difficult to do that. So we'll be making a few restrictions on ourselves to make sure that we hold true to the historical legacy of these experiments. The other goal is that we want to verify the equation of state for an ideal gas, and we'll do that by experimentally determining the value of the gas constant and then also using our data to sort of predict or forecast a value of absolute zero. And lastly, of course, we want to practice the laboratory techniques that are standard across IB physics, such as data collection and data analysis with uncertainties and things like that. Let's begin. So we want to start off with the mathematical model. So we're obviously using the equation of state for an ideal gas. So when you perform an experiment, you always want to start off with some sort of theoretical construct. So for the purposes of this experiment, we have PV equals nRT. And then you want to think to yourself, are there any linear relationships within this equation that we can exploit or take advantage of? Because linear relationships are always nice because when you make a graph of two quantities that have a linear relationship, it's always going to make a straight line. And then what's nice is you can try to find the gradient of that line, or rather, often the gradient of that line will have some physical significance as it relates to your equation. In our case, the two quantities that have a linear relationship are the pressure and the temperature, as we discovered in a previous experiment. So we can graph the pressure against the temperature, and we know that we're going to get this linear relationship. So what that means is we're going to need to, from that, we need to define or decide or choose our experimental variables. And the way it works is there's always going to be one variable that you want to vary predictably, and another one that you want to measure, and then lastly, whatever's left, you just hold constant. You've heard these called the independent variable, the dependent variable, and the control variables or the constant variables. So we're going to use the mathematical model to figure out what the independent and dependent variable are. I'll give you guys a minute to sort of look over there and decide what should we make the independent variable and what should we make the dependent variable. And remember that we're going to be using this simulation to choose our variables. So what are things that we can vary? What are things that we can hold constant? And what are things that we can measure? Okay, that was enough time to think. So the independent variable we're going to use will be the temperature. It's very easy to control the temperature on this simulation. Temperature. It's very easy to control the simulation temperature because all we have to do is just move this, heat it up or heat it down. And then we can just see up here, we can easily track the temperature up there. As a result of these changes in temperatures, we'll measure the pressure. There's that really nice pressure gauge that we can use to then see how the pressure changes in response to our temperature changes. And then lastly, that means anything that's not the temperature or the pressure, we're going to need to hold constant. So what will those constant variables be? Well, if we look back in the equation, we see that there's volume, number of particles. And R, well, R is just going to be held constant naturally because it is a constant. So we know that if we vary the temperature and measure the pressure, that we'll need to hold constant the volume of the container and the number of particles. So if we look back to the simulation, we can hold the volume constant by clicking this button, and we can hold the particles constant by just setting this at whatever value we want. So whatever you want, just put it there and just leave it at that value. Now the experiment is set up, so that's our methodology, there's our variables identified, so let's move on to the first objective. We want to figure out the gas constant. So this is what we predict or expect our data to look like, is we expect to have this linear relationship, and you'll notice that it doesn't actually go through zero. There's going to be this y-intercept, And the reason for that is because we're not using Kelvin, we're going to be using Celsius. So that's the first restriction we're going to put on ourselves, is we're going to make sure that instead of using Kelvin that we actually use Celsius. And the reason is because we're trying to mimic old experiments, historic experiments, where the Kelvin scale didn't exist yet. Let's take the ideal gas law, PV equals nRT. And what we're going to do is solve this given that we're graphing P against T. Now we know from mathematics that if you take your rise over your run, that you get the gradient. So we know that the gradient of a graph is the change in y over the change in x. As we look at our graph, the y is the pressure and the temperature is the x-axis. So all we have to do is solve this equation for those two quantities. So we'll notice that we've got our pressure here as the y and our temperature here as the x. So what we're going to do is just rearrange this equation so that it's P over T. If we do that, we're going to divide both sides by T and divide both sides by V. So we'll end up with this relationship that P over T is equal to NR over V. And that is going to be constant because look at these variables, NR over V. Experimentally, we said that we're going to hold the number of particles constant and we're going to hold the volume constant. Those are the ones that we identified as being constant. So this has to be a constant value, which is great because that means that what's constant in our graph? Well, the gradient is constant. So this will allow us to determine R, because if we can measure the gradient's just going to be that constant value. So we're going to measure that experimentally. We'll graph our data, where this is our data. So this is our data. And then this is going to be our gradient. So we could sort of construct an equation, I guess we could call it, where we could say that NR over V is going to be equal to the gradient of our graph. And from there, you can just solve this for R, and then we know what our R value is. But it's going to require us to first plot the data, find the gradient. If we solve this for R, you can see we're going to need to move the N over V, flip it, and move it to the other side. So we get that R is going to be equal to the gradient times V divided by N. And that'll be our value of R. So we'll remember this for later and we'll come back to it. This is just our theory. This is how we're going to conduct the experiment. The last thing we have to do is we have to figure out the coldest possible temperature. We know the ideal gas law, PV equals nRT, and we also remember Boltzmann's equation from our very first lesson in thermal physics, which relates the temperature to the average kinetic energy of the particles. So we have to think to ourselves is, well, what is the coldest possible temperature? And how would that represent or how would that manifest within our equation, PV equals nRT? Well, the coldest possible temperature is absolute zero. And absolute zero is where the temperature is equal to zero. Now, the gas constant can't be zero. The number of particles isn't going to be zero because we're holding that constant. And the volume isn't going to be zero. So what has to happen when we reach absolute zero is that the pressure has to go to zero. So as we drop the temperature down to zero, our ideal gas equation predicts that the pressure should also go to zero. And that makes sense, right? Because if the temperature is zero, then the particles have no kinetic energy. And if they have no kinetic energy, then they're not going to be banging into the walls of the container, exerting a pressure any longer. So this makes sense that the temperature going to zero would make the pressure also go to zero. Remember how we had that y-intercept on our graph? Well, if we forecast backwards into negative temperatures, which is where absolute zero is going to be in the Celsius temperature scale, we can actually find where absolute zero is going to be. It'll be the X-intercept. Now, finding the X-intercept can be a little bit tricky, so let's kind of review how that works. So if you have the equation of a line where y equals mx plus b, that's just the straight up equation of a line, which we know that our data is going to make a line. And we know that our y-axis is the pressure and our x-axis is the temperature. So let's replace those quantities. So the y-axis is the pressure The x-axis is the temperature. We also know that we'll have absolute zero when the pressure goes to zero. So we could rearrange this equation and it will be mt equals negative b. So I'm just going to take the b and subtract it to the other side. Now we're solving this for the temperature. So the temperature, the absolute zero temperature, is going to be negative b divided by m, where b is the negative of the y-intercept divided by the gradient. So this is how we're going to find the absolute zero temperature. We'll find the y-intercept of our data, and then we'll divide by the gradient of our data. So this is going to be found from our data alone. We're not going to need to do any, like up here where we found r, we're not going to need to substitute in the volume or the number of particles. We're just going to use it straight up from our data. Okay, that's it. That's the design of this experiment. I'll continue this in part 2, where we'll actually show how to collect the data and estimate the uncertainties.